So let's start with our magic function that will perform much better than obvious search. Let's see what that's going to be. So I'm going to call it binary search as discussed. It will take a list L and search for the element K. Let me write that as a comment here. This function is an alternative for the obvious search. It does exactly what is expected from the obvious search, but in an efficient way. What is efficient here? Okay, this method is popularly called the binary search. Okay, there's one thing that you want to really learn in this entire subject called Python. Let it be the binary search. You know, it's just magical. You know, you will see the magic happen. All right, so how do we go about it? I'm going to patiently write the code here. I want to send out a small warning message here. It might appear like once again, you know, I'm struggling. It might appear like I'm writing a longish code instead of a short and sweet and a crisp code. I'm purposefully going to write a long code here, and many people out there who want to sort of show that they can write a smaller code, be it as it may, the point is not to write a small code here. The point is to write a piece of code that you all can understand. So please bear with me. My code can be a little longer. You can always Google up and then see a code that is short, sweet, and finishes in just half a page. But then the motive is not that. The motive is to think on the fly. Okay, I'm going to patiently connect what we were discussing before on the dictionary idea, the Hema Malini example, on to search. All right. So as and always, there'll be some geek who will look up Geeks for Geeks code and then say there's a much easier way to do it. The point is not that. The point is to make you all understand. So please bear with me. Small is not always better, right? I mean, sometimes you may want to write longish code so that you explain things well. A 2.5 hours Bollywood movie can be summarized in 2 minutes, but then it's fun to watch it for 2.5 hours. Wrong analogy, bad example, but you see the spirit with which I'm saying this. All right, so without any further cacophony, let me start off with the code. All right, so what do we do now? Let me think. I will ensure that this scrolls up a little just so that you can see it. Okay. And also what I'll do is I will try to zoom this. Okay, perfect. Let me just explain a few things here. Okay. All right. So there is an array, right? Remember, there's an array. And in this very array, you will have many elements. This is your list, basically L. Okay, the list L. You have a list L. Whatever is here, L is this, and it is sorted. Okay, this is sorted. The previous obvious search, it works on any list, but what we are going to write right now only works on sorted list. So throughout the discussion, we are going to assume that the list L is sorted. Okay, you're going to remember this. Okay, all right, so let me remove that for the time being, now that you know that the list is sorted. So just in case you had numbers, let's say here 72, 81, 93, and so on. If your K were to be, let's say, some 39, okay, how will you find if 39 is present in this list or not? Okay, in this very list, you need to find whether 31 is present or not. How will you find that? I will first come to the midpoint. The idea is very simple. I'll come to the midpoint. Midpoint here, let's say, was 81, and I'll check 39 is definitely less than 81. Correct? So what I'll do is I'll now realize that this particular thing, 39, should be on the left side of this. And I can simply chop off this part of the list. I don't need this part of the list because I need to just find if 39 is present on the left side. Okay, so the point is 39, you take the left side of the list and then check if 39 is present here or not. How do you do that? Again, what you do is look at the middle element here. Middle or any element will do. Middle element seems to be a wise idea. You see, I mean, you're cutting it by half, right? Example, if you remember, right? So middle element happens to be 11 here. Then you know your 39 will be on this side. Okay. It will be on this side. 39 will be on the right side. So what you do is you chop off this side of the list, okay, and concentrate on the presence of 39 on the right side of the list, okay. And then what you do is you again look at this part of the list and then look at the center point and then see if 39 is present there or not. Just in case you see 18 here, you know very well 39 should be this place. You see, you are making the list go half in size and then half in size, and then eventually the list becomes smaller and smaller and smaller. Okay, so small, you know, when you take a number and keep halving it, you keep making that go half and half and half, you know what happens, right? So remember, so you take a very, very big number, let's say 1 million, right? Half of this 1 million is roughly 2 to the power of 20. Okay, in fact 2 to the power of 20 is 1024 into 1024, so approximately I'll call this 2 to the power of 20. And then when you halve this, when you make half of this, you get 2 to the 19, not 2 to the 10. Okay, so and then half of this will be 2 to the 18, and half of this will be 2 to the 17, and half of this will be 2 to the 16, and so on. Roughly in 20 steps, in fact indeed in 20 steps, you will make a list of size 1 million become a list of size just 1. Think about what I'm saying, right? I mean, it's a very powerful idea, but the entire thing will work. You can search through a list only if the list is sorted. You can search a dictionary, right? Let me make a note of this. This is an important point. So you can, searching a dictionary is easy. Searching a dictionary is easy. By easy I mean super easy, only if it is sorted. By sorted I mean it is arranged in alphabetical order. Otherwise it's not easy. Otherwise it's going to be very difficult, and not just difficult, I mean it's close to impossible to search where a word is in a dictionary if it is not sorted. If it is not sorted, otherwise means not sorted, it's going to be very difficult, right? So I'm going to assume that the list L is sorted, okay, and then I'm going to find the element K in the list L. Alright, so let's get going and then write a piece of code. Let me slowly think, how will my code look like? What did I do? I want to shrink my vision in the list. Basically the list should become smaller and smaller. Remember what I illustrated? Okay, I want to shrink my list. How do I do that? I will do that using a while loop. Okay, it's always a good idea to say we will do that using a, when you write a research paper, they say we should always say we. It means the reader as well as the researcher. Both of us put together, we saw that, we did that, we will take a look at this plot. Okay, that's the lesson we'll learn in writing research papers. Anyways, we'll say we will do that using a while loop. So what exactly will we do? We'll say while Firstly, the first element in the list will be 0, zeroth element of L, correct? Basically, this is first element in L, index of the first element in L, not necessarily, basically the first element in L will be L of 0, right? And the last element in L will be basically len of L minus 1. The last element in L is in len of L. Basically, I'm talking about L of len of L minus 1. I'm talking about this. Here I'm talking about L of 0. Okay, I think these comments are just complicating things, but then you will get to know what I'm trying to do as we proceed further. Okay, use a while loop to look at the list and keep halving it. Halving it is the word. Okay, so what do? I'll say while you see, let me just illustrate that. You see there is a list. Okay, I need to find the middle of this list. How do I find the middle of this list? I should take the beginning, the last, and then this plus this by 2 will give me this. So this is basically your begin, this is basically your end, and the midpoint will actually be begin plus end by 2. Correct? I should keep doing this as long as this list is big enough. What do you mean by big enough? By big enough, I mean it has at least some, let's say, 2 elements. Otherwise, it doesn't make sense. You see, at least 2 elements. So let me just do that. I'll say while the list has at least 2 elements. What do you mean by that? The list will have definitely, all the elements that L has, but your begin and end, is pointing to 0 and len L minus 1. Okay, as long as end minus begin is greater than, let's say, 0, which is, it has at least 1 element, right? Or let's say it has at least 2 elements. Okay, that will be easy. Okay, we will handle the case when the number of elements is less than or equal to 1. You see, we can always handle that separately. We'll only look at the case where end minus begin is greater than 1, which means it has at least 2 elements. Okay, so what do? I calculate the middle, which is, what is middle? Begin plus end divided by 2. Remember, we discussed that. It is the integral part of begin plus end by 2. That's what you mean by middle. Okay, let me patiently think. What now? I have computed my middle. Right now, I will check the mid element with the given element k. If this is greater than k, then k should be on this side. Correct? As simple as that. So let me write that down. That's interesting, you see. So if it's greater than k, let's say if my L of mid element is greater than k, what does that mean? Okay, if the middle element is greater than the given element k, then then cut the right side and retain the left side. What do I mean by this? I think I should annotate it once again. I mean, so for people who know the code already are finding it boring, but then this code is not meant for you if you know it already. So buzz off and then write a piece of code. This is meant for people who are seeing it for the first time. I'm just kidding. All right. So you have a list here. You have a middle point here. I say L of mid, this particular thing, if it is greater than k. This is a very big number. Assume your k is some 16 and this number happens to be some 120. Then your 16 is definitely somewhere here, which means you must retain this part and get rid of this part. Okay, how do I do that? Retain left, get rid of right. That's what I say here. As you can see, retain, cut the right side and retain the left side. Okay, so that's what I'm going to do now. Let's see how I'm going to do that. Let me keep the cursor that side. So how do you do that? I will do that by simply considering, so what should I do? I should look at this, cut the right side. Cut the right side means what? This has to be cut and this has to be retained. This was begin and this was end. You see, 1 minute, we change the, okay, this was begin was the first one, this was the end, right? So in order for you to cut the right side and retain the left side, you should simply bring this particular end here. That's all. Correct? This, if you make it end, automatically this part is ignored. Now you will concentrate only on this side. Okay? You see, most of these things are commonsensical, but when you're trying to write a code, it doesn't appear commonsensical. So what do? I will simply make my end become equal to my middle minus 1. So begin remains the same. You see, the begin part, you know, it was like this, the mid was here, the begin remains the same, but the end which was here, you bring it here. And you make end to be this, so you concentrate on this region. So end will be, if this is mid, end will be 1 before that. So it is mid minus 1. Alright, so far so good. It's mid minus 1. But then what we should probably do is come up here and check if L of mid is indeed equal to K. Correct? As I'm saying, these kind of things, as you're programming, you should realize, you should fix all the problems as you're programming. I just realized that you should once check if the middle is actually K. If it's K, then you return 1. Okay? Compute, wait, let's stay organized. Compute, I'm a little particular about grammar, so compute C capital. Compute the mid, which is the midpoint of begin to end, which is given by this formula. We saw that in detail. You see, so when there are even number of elements, you know, there can be 2 middle elements, right? So we realize that we'll call the left one as the middle, if you know what I mean. If it's confusing, don't worry, I'm just computing mid here, that's all I wanted to say. So if L of mid is equal to K, I'll return 1. Okay, if this is not true, then the middle one was not K. We'll go ahead, okay? And then if L of mid is greater than K, then end equals mid minus 1. Okay? What if this is not true? If L of mid is less than K, right? I can as well put a else here, but I prefer not doing that. You know, sometimes it's easier on the mind to not put else. Else means if this doesn't happen, whatever happens, execute that. Somehow, as a programmer, I have always realized that not using else as much as possible helps. You know, so what have you done here? If it's equal, you have seen it. That's all, right? If mid is indeed K, rather L of mid is indeed K, then we return true, which is 1, and stop the code. Okay? If not, then we go ahead. If L of mid is greater than K, end equals mid minus 1. Okay, I'm going really slow here. These 2 lines are very important. Just concentrate on these 2 lines. They're very important. Once you're through, you go ahead. You pause and then think. Similarly, if L of mid is less than K, okay, L of mid is less than K, okay, some of you are not following what I'm doing. So let me write the comment once again here. Okay, if the middle element is less than K, okay, is less than K, then cut the which side? Because it's right here, you just cannot say it is left here. Okay, it should be there in your mind. So let us work it out. Again, the same old thing. I mean, I can do a repeated chanting of this very concept. It's all worth it because it should be easy in your mind. Okay, so this mid here, this mid, Okay. L of mid, this very element, if it's less than k, okay, then your k, if it is there, it will be on the right side of this. Then what you do, you discard the left side and you retain the right side. So discard left, retain right, exactly the opposite of before, right? Okay. If the middle element is less than k, then cut the left side and retain the right side. Okay, comment this. Of course, you can put a triple quotes too, but I don't want to do it. I like hash. So what do? You, just in case L of mid is less than k, you retain the right side and cut the left side. What do you mean by that? What do you mean by retaining cut the left and retaining the right? It simply means that this was begin, this was end. Bring this begin here. Make begin immediately after your mid. This was your mid, you see. Remember, this was the mid. Mid plus 1 will be your begin. That's all I need to type here. Okay, let me type that here now. Okay, so your begin simply will be mid plus 1. That's it. Okay, the code is almost over. Alright, so let me just see what has happened here. Let me think aloud. Binary search, you take a list L and search element K. What do? The beginning element is 0, the ending element is len of L minus 1, the last index basically of the list L. And then while, what does it mean? Use a while loop to look at the list and keep having it. I'm looking at the list, okay? End minus begin is greater than 1, okay? The list keeps shrinking, you see. It keeps shrinking, it keeps shrinking, it keeps shrinking. Whatever it is, whatever is the list, okay, whatever is the list. What I want to do is, I want to see if begin and end, wherever that is being pointed, begin and end, this region is my region of interest always. That should have at least two elements. At least two elements. If not, it's not interesting, is all I'm saying here. Okay, end minus begin is greater than 1. Good. So, and then I compute mid. Mid is simply the midpoint of that region of interest. Region of interest basically is from begin to end. Okay, and just in case the entry in the middle is k, then your job is done. You leave home, right? You're done. You have found the element and you return 1. If not, then the L of middle element is greater than k or is less than k. Correct? Let me scroll down. It's greater than k or is less than k. If it's greater than k, what do? If it's greater than k, all you do is you pull the end, okay? Make end come to the middle, okay? That's because your region of interest then will be the first half, not the second half. So then you cut the right side and retain the left side. If the middle element is less than k, which means, as I told you, I'm not going to write it once again. I wrote it some dozen number of times. I cut the left and retain the right. Think about it. And that is done. How do you cut the left side? You cut the left side by making begin, bringing begin from this end to the middle. So middle one, definitely it is not there. We have checked it. If we are outside this, it means that L of mid is not k. So I start with mid plus 1. Begin is mid plus 1. Rehearse this properly, think about it, and only after understanding this we'll go ahead. So what next? I come out of the while loop. This is outside the while loop. If we are here, it means that we haven't found the element. Also, if we are here, it means that the while condition is violated, which means, what does it mean? End minus begin, it means end minus begin is not greater than 1. it is equal to 1. That is when you come out, or it can be less than 1. Okay, which means end minus begin is either 1 or 0 or -1 or -2 or whatever. Okay, it is less than or equal to 1. Okay, what if it is equal to 1? Okay, let us just check. Now, if it is equal to 1, what is equal to 1? Let me just think. What am I doing here? I'm saying if you're outside the while loop, it means that end minus begin is less than or equal to 1. Let's say it's equal to 1. What does it mean if it's equal to 1? It means that begin equals end. Okay? It means begin equals end. Only then end minus begin, which it means if it's equal to 1, what am I saying? If it's equal to 1, then there is exactly one element in the region of interest. Okay, let me illustrate that. See, we all get confused, so it's okay to be confused, but then the point is we have to clarify our confusion and move towards clarification. Alright, so if end minus begin is equal to 1, then let's say end is some 20 and begin is some 19. Only then end minus begin will be 1, which means the region of interest starts here and ends here. So simply there are two elements, 19th element, 20th element. Only two elements are there. Right? Okay. So in that case, what should I do? If it is equal to 1, then there is exactly two elements. I'm sorry, there are exactly two elements. Okay. Then I check if L of begin is equal to K or L of end is equal to K, return 1. Okay. Else return 0. So if we are here, we have the region of interest with only two elements, and we check those two elements. Either the begin part should be only there is a begin and end, okay, and end is actually one more than begin. Okay, I'll check if L of begin is K. If it is true, then I return 1, or if L of end is K, I return 1. If it is equal to 1, then this happens. What if it's not equal to 1? What if it's equal to 0? Still this condition will check for L of begin. If end minus begin is equal to 0, then begin will be equal to end, you see. Think about it for some time. Okay, all the cases that this covers. Alright, so what if begin and end is such that, one moment, begin is 19, I said, end is 20, then the difference is 1, it comes outside the loop. Then I check L of 19 and L of 20. Okay, fine. But what if begin is 19 and end is also 19? In that case, I will check L of begin once and L of end once. L of 19, I'll check it's okay, it's redundant, but still the code works. In either case, it will be 1 if it's equal to K, and I'll return 1, right? And what if there could be a situation where begin can become more than end? That can happen actually anyways. If it happens or if it doesn't happen, I don't care. Just in case that happens, assuming that my begin is greater and end is smaller. Okay, even in that case, I'll check L of begin and L of end and then return 1. That's if it's present. Otherwise, I'll return 0. Okay, perfect. So let me now go ahead and try to execute this. Okay, what I will now do is try zooming this out just so that it's all visible in one screen. The font may appear a little smaller, please don't mind. I'm going to restart this. Then say import search and then search, you see. One function is obvious search, one function is binary search. Okay, question mark, it will give you the details of this function. The function is an alternative for etc, etc. Okay, good. So I can search for binary search in a list L. Okay, so let me just first create the list L. What was my list L? L can be anything. Let's say 12, 15, 100, 121, 1001, 24, 2016, 2021, which is this year. Okay, so now I can try to search an element here. Oh, very good. It did not throw any error. I mean, there was no problem, absolutely. In fact, it got executed. I thought there would at least be some logical error. It's working perfectly fine. 151 is not there, so it says no, 1024 is there. Let me enable cursor. 1024 is there, and so it says 1024 here, right? And let me choose 2021, and it shows 1. Perfect. But the list is very small. I want the list to be very big. So what I'll do is a list of range of this is 1 million, right? 1000 times 1000 is 1 million, times 100 is 100 million. Okay, this is easy, you see. I mean, to create a big list that is sorted. In fact, you can create a big list that is not 0, 1, 2, 3, 4, 5 up to 100 million, minus 1 of course, which is sorted. You can create some random numbers there, but that's a lot of headache. I'll not do it. So a program that works for this should work for anything else. So let me now say search binary on L. Let me try finding a random number like this. It should be there, because why? What is L? You say L is all numbers from 0 to 100 million. Let me print L and show it to you. Okay, it will go on and on for the entire day. It will even take some time to start. Oh God, why did I even execute this code? Right. Okay, it will go on and on and on. Anyways, meanwhile, let us come this side and try to see that we have obvious search here, right? And we have binary search here. Correct? Obvious search took some time, no? We used that import time function and tried doing something. Let's try doing the same thing for binary search too. Okay? And see if it, I think our friend will not stop. So I will cancel it. There's a keyboard interrupt that you can do by pressing Ctrl C on your system. That's what I did. And let me clear the screen and then say import time. Okay? What I'll do is, maybe I will try to zoom this, increase the font, and my L is already there. In search, if I say obvious search in the list L, I want to find the number 10, it does very quickly. But what if it's a very big number? You see, maybe something that is not even here in the list. Okay, then it takes a long time, right? We saw that it was quite some time here. How did we do that? We did the following. We said import time. What was that code? A equals time, correct? And then we did print search obvious search L -1, something that is not there in the list, and then B equals time. I hope I'm writing the same thing that we wrote long back, and then I'll say print B minus A. Okay, the time after minus time before. This should give me time that it takes. It was how many seconds? So it takes 2 seconds for this. All right. Okay. So instead, let me do this for the binary search. Let's see how much time it takes. Did you see the magic? It did not take any time. You know, as I executed it, boom, it comes. Right? Whereas for obvious search, you see, this is not binary search. Obvious search, if I'm executing, it is taking time. That's because, why is this happening? That's because, One second. That's because in the obvious search, what's happening is the following. It goes through the entire list. Is it here? Is it here? Is it here? Is it here? Goes until the end. It is not here and then declares 0. But then in binary search, the halving principle, you see, dictionary searching, give up on this, give up on this, give up on this, give up on this. Quickly the list becomes small, and very quickly we decide if the element is there or not. Is quickly decided in case of what? In case of binary search. But in case of the obvious search, it takes a long time. We just saw that. Okay, let's play around just a little more. Okay, let me just remove this. And yeah, so what if I want to do the obvious search of some element which is there in the list? What is that? Which is I think okay, wait a minute. What was the let's fix a k so that we put the same k and then check it. Let me. Okay, so what I'll do is k equals, what was the number? Length of L is how much? Length of L is so much. Let me clear the screen for you people. Okay, so length of L is so much, which means the last element of L will be so much. Okay, I'll call this as k. Okay, len of L minus 1, the last element, which means this element, whatever is in k, whatever k is denoting, that number is actually there in the list. Okay, now let's do the obvious search and try to find not -1 but k here. I hope you all know what I'm doing. Let's find k here, and it takes time because it should go to the end of the list. But if you were to find, instead of k, which is 999, 999, 99, if it is some 10, it will execute in no time, right? It is what 0.0006 seconds, because it's in the first part of L. Even obvious search works there, because is L of 0 10, is L of 1 10, is L of 2 10, so on up to L of 10 10. Very quickly it executed. Okay, even binary search will be fast here, obvious search will be fast here. But then if you put a k here, we saw, right, k or -1 here, a number which will make your obvious search go through the entire list. It takes some time, it takes some non-trivial time, you see. But then let us try, I'm just going by the history, up arrow gives you the history, a binary search, okay, for k only, L comma k, you see that it's really fast. Okay, let us see more magic now. Okay, what did we do? Let me repeat it. Obvious search, okay, took 2.7 seconds, and binary search took no time, right? 0.0002 seconds. Now what I'll do, I will write L as list in the range, make it 1 billion instead of 100 million. I must warn you, this is going to take some time. Okay. Anyways, I believe, I don't know whether the editing team has edited the time that it takes in between. If they haven't edited, it is good, because you people will get to know how much time it actually took to create the list. Also is not so easy. 1 billion entries, it's populating with 0, 1, 2, 3 up to 1 billion. Okay, it will take a few seconds of the order of some, I think it took some 20 seconds here, right? Now, let me say k is equal to -1, which is not here. Okay, of course it is not being displayed because my keyboard is not working because the system is hung. The monitor is not displaying anything. It will take some time. That's because what you are doing here is very expensive. You are using the whole of your memory for this list. Okay, if you open your activity, I mean whatever, if you're on Linux, you can try to see your memory resources. If you are a sort of a geek, you know how to do it. It will show that you are using all your what is called RAM memory for this. I hope it comes out. Okay, let's wait. Now, because this is really elegant, very beautiful, it's worth waiting. Okay, k equals -1. Okay, good. It took so much time for this one line command. That's because it was stuck basically. Okay, now let me go ahead and execute this binary search and an obvious search on this. Okay, and see the time that it takes. Okay, we got to be patient. It may take around a minute's time, if I'm not wrong. Let's see. Waiting. There is some way in which we can see a time in this shell. Oh, because this is the time right now. Okay. Of course, this is of no use because I'm computing. Oh, it took to 22:45, 10:45 p.m. it is. All right. It's taking its own time. Let's wait. Oh, 33 seconds. Please observe, we are in the climax point of today's discussion. Right? It took 33 seconds for us to run the obvious search on a list with how many elements? 1 billion elements, where k was -1, which is it did not belong to the list. And it should obviously say 0 because it did not belong. Now, what next? We will try our binary search on this. Okay? Alright? What was that? You see, where is 33 seconds and where is 0.0002 seconds? I mean, mole and mountain difference. Do you observe that? Mole and mountain difference between this obvious search and the binary search. Super duper different. You cannot even believe 33 seconds is close to half a minute. Okay? But note, let me just write this down. This is really nice to think for a minute, sort of let's meditate on this. This was your obvious search and this was your binary search. Point to note, both of them used your computer. This very same computer it used. My very computer. Alright? But this one used a technique. This one used some other technique. Alright? And this technique had an upper hand over this technique. Okay? This had an upper hand over this technique. What does it mean? It simply means that the technique you use to search can in itself can be the technology. An English expert who sees this sentence will say, what is he talking? Technique is a technology, it seems. Of course, technology is derived from technique. The study of techniques is called technology. No, by technology I mean the hardware technology. I'm using a super duper computer, but in the very same super duper computer, the technique that I use matters. 33 seconds and then 0.0002 seconds. Same list, you see? Same list, same key element, okay? But the method that I'm using is different, okay? And that's what is giving this significant difference. Okay, in fact, a very beautiful thing to observe here is no matter how big the list is, binary search is super duper fast. Okay, in fact, let me just make a note of this. It's a wonderful fact that if you were to list everyone in the world, every single person ever lived in the world, okay, create a telephone directory for that person, okay, with all the entries, and if you keep it in alphabetical order, okay, alphabetical order. If this is in alphabetical order, what am I saying? I'm saying that you take every single person ever lived in the world and then create a telephone directory of this, of all these people. Searching that will not be very difficult. Searching is very easy if you use the binary search technique. Whatever we illustrated right now. No matter how big the list is, how big the repository is, binary search really rocks. So it is the technique Also, apart from the fixed technology, you cannot better, in fact, you use a super duper computer to compute this using this algorithm, and you use a very old computer from the 80s to compute to which runs binary search. Okay, this will still beat your modern computer, right? Because the technique that you're using matters. All right, long story short, your algorithm matters. What was the algorithm? Let us take a look at the algorithm once, because it has worked like magic. Although slightly big here, binary search tried reducing your space of less, all the elements L, the region of interest shrunk by half and half and half, and very quickly you could see whether K belonged there or not. The code was so very simple. Okay, try doing it. Anyways, I hope you all enjoyed this piece of code. First time we wrote some non-trivial code, quite long code, and then quite deep in logic. Maybe, as and always, it's not easy to get something in the first run. You may have to go through it again and again. All right, so try coding with me a couple of times, redo the video, rerun the video and redo the code, and it will be very clear to you. If it's not clear to you, as and always, we are there to help in live session or on the forum. Thank you.